Oh, hold on. Yeah, thank you for that introduction, Dimitri, and thank you for having me. I'm very excited to be with you all, if only virtually. One note, I actually don't know where the Zoom chat is currently, so if you put a question there, I won't see it, so please just interrupt verbally during the talk, or you can always save your question to the end if you don't want to interrupt. All right, so this talk I'm going to give today is based on a paper that came out on Archive about a year ago and was actually published a little bit after that. And it's about electric field screening and paired discharges and generation of pulsar radio emission. So this is a collaboration with Sasha Filipov and Andrei Timokhin. So I think we have a general kind of plasma background today. So I'll start by telling you all what a pulsar is. Pulsar is a rapidly rotating magnetized neutron star. So you can see an image of the nebula around a pulsar with the pulsar at the center on the left side of the slide. So a pulsar is a highly magnetized, rapidly rotating neutron star. It has about a 10-kilometer radius, and its mass is about 1.4 times the mass of the sun. These stars are very highly magnetized, so it has a magnetic field about 10 to the 12th Gauss. So this is really very significantly higher than the magnetic fields you are typically looking at if you're a laboratory plasma physicist. These things spin rapidly with a spin period of 1.4 milliseconds to 8.5 seconds. They're called pulsars because they emit pulses of radio emission. There are about 3,000 known pulsars. So there's several aspects of pulsar physics that are interesting. And the one that we're going to talk about today is the coherent radio emission that's produced in the polar cap. So you can see on the left side of this slide an artist's depiction of a pulsar, where at the center in orange, you have a neutron star. And then in blue, you have magnetic field lines that trace out the pulsar magnetosphere. And you can see in the polar regions of this magnetosphere, there's a light purple glow. And this is meant to represent the radio emission that occurs in the polar cap. So many aspects of this emission are unexplained. And in this talk, we're going to focus on two. One is the luminosity of the emission, and one is its spectrum. So the first of these, the radioluminosity, we can see some observations of this radioluminosity on the left side of this slide. So this is a plot from an observational paper where along the x-axis, you have a spin down luminosity. This is, you can think of it as sort of a rough measure of how much luminosity is kind of available to all the processes in the pulsar. And along the y-axis, you have the radioluminosity. So the different dots in this plot are different types of pulsars, and the lines are a fit that the observer who wrote this paper wanted to do, but it's not super important to us. The main takeaway message that you should get from this plot is that most pulsars have a radioluminosity between 10 to the 27th to 10 to the 31st ergs per second. And it's not really known why this luminosity has that magnitude and not some other magnitude. Another aspect of the radio emission that's unexplained is the radio spectrum. So on the left side of the slide, you can see a spectrum from a particular pulsar, where along the x-axis you have frequency, and along the y-axis you have energy observed at that frequency. This pulsar has a spectral index of -1.4, making it actually a fairly typical pulsar. Because if you take an ensemble of several pulsar observations and find sort of an average spectrum from those, you get something that's in the green box with the spectral index like this one that we have for a particular pulsar, but with a big scatter on top of it. And it's not known why this spectrum is as it is and not something else. To understand these aspects of the radio emission, we have to consider what's happening in the region where the emission is produced.
Libby,
Yeah.
Can I interrupt with a question which you can refuse to answer because it's kind of way out of the scope of this talk, but you've just described things that we don't know about the radio emission from pulsars. Can you quickly say when they were first discovered, why? I mean, I think since they were shortly after they were first discovered, we've known that the radio emissions are from spinning neutron stars. Can you quickly say are there strong reasons for that?
Why the emission is from rotating neutron stars? I actually don't know what the sort of fundamental reason for
Yeah,
that.
okay, that's fine. I realize I also don't know, so
yeah.
Go ahead.
Okay.
No, well, sorry. So, I mean, it has to be something very compact because of the period, right? Rapid period of like second long. So that already indicates that it's something small in size. But I guess maybe that's the main reason. So and also because they are because they are observed in like the crab at the center of a supernova remnant, right? So it's a remnant of an exploding star, of a supernova. So it could be either a neutron star or black hole.
So it was mostly the period and not so much the specifics of anything specific about the radio emission.
Well, the radio emission is the least understood, but I should
yeah.
I
mean, I think talk. Yeah, I think Dimitri's right. I mean, the radio emission, it's a big mystery, like how it's created. I mean, this whole talk is sort of premised on one explanation for how it's created, but it's not accepted by everyone. So it's yeah, I don't think you could use the radio emission to prove anything else really when you don't understand the emission itself.
Thanks.
Yeah. Okay. So to understand the emission, we have to sort of understand what's going on where the emission is created. So this is in a plasma, basically. So basically how a pulsar works is you have a neutron star, which we have in orange here, and it's threaded by magnetic field lines. And then this thing starts to rotate, or is rotating rather. And a rotating magnetic field will cause a polarization of the neutron star. So this is the same mechanism as the mechanism that occurs in a Faraday generator, if you're familiar with that. So you'll get a buildup of charges on the poles of the neutron star. And this polarization will cause a strong electric field outside of the star, which you see in red. This electric field will extract charges from the star surface, and these primary charges will cause the creation of additional charges via a cascade, which we'll describe later. And this results in the creation of a plasma around the star. So the plasma magnetosphere that exists actually is a really complex structure with several interesting phenomena. So you can see a diagram of the pulsar magnetosphere on the left, where I don't want you to try to understand everything that's going on here, but the point that you should take away is just that it's very complicated, right? So you have current sheet, you've got a Y point, you've got closed field lines, you've got open field lines. But the place where the radio emission is produced is this polar cap region, right? And here the magnetic field lines are going to extend all the way out to infinity. And in this region, plasma will be periodically created and then leave out to infinity. All right, so that's where the emission is produced. And in this talk, we're going to study this emission and try to give insight into two different aspects of the emission that aren't fully understood. So that's the radioluminosity and the spectrum. So the talk will have two parts. The first part is a discussion of the polar cap discharge, where the radio emission may be produced through the screening of the electric field. And then we'll talk about three important and one unimportant stages of electric field evolution in the polar cap discharge, with implications for observation of each. So we'll talk about a screening stage, a nonlinear stage, frozen stage, which is sort of a numerical artifact, and then there's a linear stage. All right. So let's start by discussing the pair discharge that might create the radio emission. So if we go back to our artist depiction of the neutron star, and we've got this polar cap region that we're interested in this region, you're going to have the strong inductive electric field, which we discussed earlier. And this is going to create a complicated pair discharge. So again, I have this fairly complicated diagram on the left side of the slide, which comes from a paper by one of my collaborators. And you shouldn't attempt to understand this diagram, but the point is just that the discharge that occurs in this region is actually really complicated. But you can't, to understand a complicated thing, you have to simplify it. So that's what we're going to do. So we're going to take a lot of complicated physics and make it simpler. So you have a neutron star surface, and then you have magnetic field lines coming out in blue. You've got your strong inductive electric field in pink here. And the discharge that will happen in this region will occur as follows. So first, the electric field will accelerate electrons from the surface to a Lorentz factor of roughly 10 to the 7th. These primary electrons will curvature radiate gamma rays because they're moving along curved magnetic field lines. These gamma rays will be absorbed in the magnetic field, and as they're absorbed in the magnetic field, a QED process will continually create lower energy pairs with a Lorentz factor of roughly 100. Now, these lower energy pairs will be able to interact with the electric field in a way that the initial population of electrons extracted from the neutron star surface won't be able to. And in particular, these secondary pairs will try to screen out the electric field. So the positron will get turned around and the electron will get more accelerated. And they'll do that. They'll try to screen out the electric field. They'll overshoot and then they'll come back. So this process will set up waves that occur in this pair plasma that's being created. And as this process goes on, more and more lower energy pairs will keep being added to the system by this QED process. So these waves will occur in a plasma that is getting more and more plasma added to it, and this process will damp the waves. Now, these plasma waves will eventually be able to escape the cloud of pair plasma that exists in this region as Poynting flux, and they could become the radio emission that we actually observe from the pulsars here on Earth. So one of my collaborators did some simulations of this process that we can look at the left side of this slide. So this is a 2D simulation of the polar cap plasma that will show electromagnetic fluctuations and Poynting flux. So you can see we've got our neutron star surface in orange. And then I have an x-axis and a y-axis. And you can see that if you simulate this process, you can get a cloud of plasma being created, which you see in the first plot. And then you see electric field along the direction away from the neutron star. You can see fluctuations in this electric field. These are being set up as the initial electric field is being screened. And then you see magnetic component as well. And together these create a Poynting flux, which you see in the final plot. And this Poynting flux can escape as light. Now, this is a very two-dimensional process, obviously, but it's important to note that the pairs themselves only move along the magnetic field in the x direction, so sort of away from the star. So this means that the time evolution of the fluctuations is controlled by the parallel dynamics. So you can see the Maxwell equation in this purple box, right? This is giving the evolution of the magnetic field and the electric field, but it's all controlled by a parallel current, Jx. This means that the evolution of the radiation amplitude can be studied approximately in one dimension just by looking at the interaction of a parallel electric field with newly added pairs. So this means to get some insight into the radio emission process, we can take our already simplified picture of the pair discharge and simplify it even further. So take the first black box and you go to the second black box. So basically, to understand the overall physics of this process, we can look at just an electric field in a vacuum and then dump pairs on it by hand in a PIC simulation and see how this situation evolves. So that is, we'll model the discharge evolution by the screening and damping of a vacuum electric field by continuous creation of Lorentz factor 10 small temperature pairs. So we can see what happens in a situation like this in a PIC simulation at right. So in the first plot, we have the normalized root mean square electric field in a PIC simulation box versus normalized time. And in the second box, we have the normalized pair density versus normalized time. These normalizations are just taken to be sort of the natural ones for this situation. Some people have asked what the numerical values of the normalizations are, and if you're curious, I added a bullet point on that at the bottom of the slide. But in any case, you start off with a strong unshielded electric field and no pairs in the box, and you add more pairs. So these pairs are meant to represent the pairs that would be produced in the real pulsar through a QED process. So you just have a density that increases. And in response to this increasing plasma density, the electric field will be screened to 0, and then it will start to oscillate as you see in the pink line. So our work is going to be building analytical models of the screening and damping process and comparing them with these simple PIC simulations. And these analytical models will allow us to explain the luminosity of the pulsar and give a little bit of insight into the spectrum. And I'll note that some inspiration for this project came from analogous but different physics of plasma wave heating in tokamaks.
And Libby, can you remind me, these are 2D simulations?
So these are just, it's basically just a one-dimensional setup.
Okay, just along the magnetic field.
Yeah, exactly. But the physics that occurs is analogous to the physics that occurs in the two-dimensional simulations that Sasha did. So you sort of get at the essence of the two-dimensional physics, even in one dimension.
Thank you.
So we'll identify 4 key phases in the damping of the electric field. So here I've repeated the plot of the electric field that we had before, and there's 4 key phases. So the first phase is a screening phase. This is when the initial electric field gets shielded out in the discharge. This particular phase has actually been, studied by other people in the literature before us. But then the more interesting phases are a nonlinear phase, and this is phase 2. And in this phase, there's very strong damping of the electric field. And in this phase, we'll see that newly added pairs are fully reversed by the electric field. Oh goodness, the power on my laptop is low. Just a second here. Should have plugged this in earlier, but we'll get it set. All right, everything's good now. So in this phase, we have strong damping, which occurs because newly added pairs are fully reversed by the electric field. So if you drop a positron, it'll get turned completely around in this sort of direction of the electric field, and the electron will get very dramatically accelerated in the way it was going. After this, there's a frozen phase. This is an artifact of the simplified setup in our simulation. And it ends eventually, and this is not expected to occur in a 2D setup, so it's discussed in the paper, but we don't need to discuss it here, really. Then finally, there's a last phase, which is a phase of linear waves and weak damping. In this phase, new pairs are not fully reversed by the electric field. They just get their momenta changed a little bit. All right, so to actually understand the physics going on, we have to know the equations that govern our system. So since you guys are all plasma physicists, this is a pretty boring slide for you, but I often give this talk to people who know no plasma physics. So here it is. So we have a Vlasov equation, which looks like, the Vlasov equation that you have normally. I've normalized this equation appropriately to our system. But the slightly novel aspect of this Vlasov equation is you have a source term, right? So you're adding in pairs at some momentum UL. So those just become a source term in your Vlasov equation. Then you have Ampere's law. And then you define a plasma current, right? So when you take the normalizations appropriate to our system, which you can see on the right side of the slide, you find that actually the only parameters that kind of survive are two ones. One of them is UL, so this is the momentum of the freshly created pairs. So the value for this in an actual pulsar is about 10 to 1,000. And in our simulation, we just take 10. And then there's this parameter Psi, which appears in the definition of a current. So this is just the energy in the initial electric field divided by the rest mass energy in pairs injected in a unit time. So this has a value of roughly 10 to the 12 for typical pulsar parameters. We use a smaller value in our simulation just to compare with our analytics, but you could use a larger value. It would just take longer to simulate.
Is this electric field then is it electrostatic?
Yeah.
Does it have,
so
it has no curl?
Right, exactly. So in our simplified simulations, it's electrostatic and you've got no curl, as you say. Of course, that's not the case in the two-dimensional situation, and you need electromagnetic waves to actually get, something that can escape as light. But again, the idea here is we take the simple electrostatic 1D situation, and it has a lot of physics that also occurs in the more complicated two-dimensional setup. You can also combine the previous equations to get the evolution of the electric field in terms of a relativistic plasma frequency. So this first equation in yellow should hopefully look very familiar to you since you're all plasma physicists. It's just a normal equation for a plasma oscillation. The thing that might be slightly unfamiliar to you, if you don't normally work with relativistic plasmas, is that the plasma frequency is a little bit different from the normal one. So you've got a dependence on plasma density, of course, but then you also have a dependence on the average value of 1 over Lorentz factor cubed in your plasma. This is something that you never have to worry about if you're not doing relativity, but it's very important in the relativistic plasma, as we will see. All right, so we can use these equations to understand the important phases of the electric field screening that we identified in our simplified PIC simulation. So the first phase is a screening phase. In this phase, the initial electric field is shielded out. So pairs are accelerated quickly to almost the speed of light. And, with that knowledge, you can calculate a screening time for the electric field, which goes like the square root of psi. So you can see that the electric field will go to 0 for the first time at a time that goes like the square root of psi. So if we refresh our memory of the definition of this parameter, we can see that the screening time is longer for higher initial magnetic field strengths. This is because a pulsar with a higher initial magnetic field will have more energy in the initial electric field, making it more difficult to screen out. We see that the time is shorter for higher multiplicity. This is because pairs are injected more quickly and can more effectively screen out the field. We'll see that the time is shorter for higher period, and this is because less energy is in the initial electric field for a higher period pulsar. So in this stage, you can also solve for the pair distribution function analytically from the Vlasov equation. This is not that hard, but you can see basically simulation data and analytic solution in this plot as a function of momentum for the positron distribution. And this distribution function could be used to roughly model the spectrum of particles black flowing to the pulsar surface in studies of X-ray hotspots observed by NICER, which is a mission that looks at pulsars.
Just to clarify for plasma physicists, NICER is what? It's a telescope, right?
Yeah, basically. I mean, I'm not an expert in NICER, but they're basically trying to image these.
It's a hard X-ray
that occurs under the polar cap or at the polar cap of the pulsar, right? You get basically, so when this discharge occurs, some of the particles will fly back at the surface, heat it up, and then that'll radiate and create this hot spot, and that's observed by NICER. And so when people try to come up with models for this emission, they have some model for the neutron star surface, and then they need some distribution of particles to fly into that surface. So you could use a model like this for that work if you wanted to. All right, so after this, we will move into a nonlinear stage with strong damping when newly added pairs are fully reversed by the electric field. All right, so to understand this stage, I will bring back the plasma physics equations that we had earlier. So you have an equation for the oscillation of the electric field in terms of a plasma frequency with the relativistic components. So as you can see from, all right, so let's take a look at what the electric field is doing. So here I have the average electric field in the box, the bottom left side of this slide. So before I had root mean square, so everything was positive, but this is quite similar, but it goes negative and positive. So you start off with an average electric field that's negative, and then it gets sent to 0 in screening, and then you've got these oscillations with a decaying amplitude. So you can see from the first equation in blue that to understand how this electric field evolves, we need to understand how the plasma frequency behaves in this period. So you can see the plasma frequency in purple and the first plot here. Right, so you see the plasma frequency as a function of time. And the first thing you should notice about this purple line is that it's got these huge spikes in it. That's the most notable aspect of its behavior. So these spikes are clearly important to the overall damping that occurs. So let's try to understand why this spiking frequency occurs and how it might affect the electric field evolution. So I'm going to repeat my plot of electric field and frequency on the left side of this slide. And we can look at one particular oscillation of the electric field, which is called out by the region not in brown in this plot. So to understand the frequency, we have to understand the plasma distribution function in this time period. And I have a movie of how this distribution function occurs, how this different distribution function behaves in the time period in white on the right here. And I will attempt to play this movie once, and then we'll play it through again and discuss it. All right, I think I've got to change my cursor to do this though. Yeah, okay, there we go. So I'll play this through once and then we can discuss it. Okay, so that's kind of cool. Let's start it again. All right, so basically on the x-axis of this plot, you have the momentum of the electrons, and then you've got the distribution function on the y-axis. So this movie is going to start out at the beginning of the white period here. So at this time, the electric field is near 0. So when you add these freshly created pairs to the system, they won't be pulled anywhere much because there's not really an electric field there. So they'll create this buildup in phase space here, right? So these are all newly added pairs that are being added and they're not being dragged. So they're just building up and making a chunk, sort of like a bump in the distribution function. But as time goes on, the electric field will increase, and this increase in the electric field will pull the electrons in momentum space through momentum of 0, and they'll be moved into the other direction, right? So basically, you've got a bump in the distribution function, and then it gets pulled through u of 0. So what this will do is create a very large spike in the frequency, right? Because the frequency goes as the average value of 1 over Lorentz factor cubed in the distribution function. This gets larger when the average Lorentz factor is smaller. And one great way to make the average Lorentz factor smaller is to have a big chunk in your distribution function that gets pulled through a momentum of 0. And that's what happens here. So this bump getting pulled through 0 is what creates the spikes in the plasma frequency. All right, so that's the important part of the distribution function evolution. You can also look at how the electron distribution function continues to evolve as the electric field continues to oscillate. You can see the bump getting formed here, getting pulled through momentum of 0, and then it sort of keeps going, right? And right, there's not that much you can say about this aspect of the physics, but it does look nice. So when Heike Hakobayan, who is the developer of our PIC code, saw this, he thought of an ocean wave. So I decided to put in a picture of an ocean wave here, just as sort of an artistic interlude.
Libby, I have a question, if you don't mind.
Yeah.
You said that the pairs are injected with a Lorentz factor of like 10 to the 2 or something, right?
Yeah, anywhere from 10 to 1,000, basically.
Okay, yeah, but in the, like, at the start of the videos, it looks like they always have slightly positive momentum. Am I just reading the plot wrong, or do you actually inject them with, like, when you inject the pairs, do they have, what's their initial momentum?
They get in
simulation,
it's injected at a momentum of 10, right? So
okay, so it's not going all directions.
Oh, yeah. Well, it would be injected in this manner. You'd have some sort of probably thermal spread, I guess, on the injection, but it would be all sort of going in one direction around a momentum of anywhere from 10 to 1,000.
Okay.
Yeah. Okay, so the effect of this spiked frequency will be to damp the electric field. You can see how this damping occurs in either a mathematical way or a physical intuition way. So we'll start with the mathematical way. So I'll repeat our frequency plot and our electric field plot. And here's our equation for the electric field evolution. You can see the frequency is very strongly spiked, so you can just represent it as a delta function, right? So I'm just gonna take this purple thing, collapse it down to the red one. So this is a delta function that's occurring at a time that's slightly removed from the time at which the electric field goes through zero. So that's the time that the electric field goes through zero is capital T naught hat. So this is going to occur at time delta after that time of zero. Okay, so if you take this equation, you can integrate it, and you can get out an equation which relates the derivative of the electric field at a time after the spike with a derivative at the time before the spike minus the value of the electric field at the time of the spike. So that's a lot of different times, but basically you're going to take an initial derivative before the spike, which you see in green here, and it's going to get pulled down to something like orange here. And so reducing the derivative will mean that the amplitude of the next oscillation of the electric field is smaller, and that's going to correspond to damping. So that's the mathematical explanation for why this damping occurs in this stage. But the physical mechanism is just the reversal of the newly added pairs. So in this situation, when you dump new pairs on the system and they get turned fully around, that's a very violent process. It takes a lot of energy to take something relativistically moving in one direction and move it relativistically in the other direction, right? When you have an oscillation, that overall oscillation has an energy budget. So there's energy in the fields that are oscillating and in the particle motion. And basically what's happening here is you're adding new pairs to the system. They're getting ripped around very violently. And the energy for that action has to come out of the energy of the electric field. So this gives you a very strong damping in the electric field amplitude. So that's the physical mechanism. All right. I've already seen this video several times. So I'll note that an analytic estimate of the effect is possible. So we do this in our paper, but just to briefly outline it, the damping can be analytically modeled by solving the Vlasov equation for a sinusoidal field to get a form for the distribution function, numerically solving for the average value of 1 over Lorentz factor cubed, and then evaluating the damping strength. So you can see our analytic form for the distribution function on the left side of the slide. It agrees well with the simulation data. And the damping that we derive also agrees well with the observed damping in the simulation. So basically you find an exponential damping with a strength that depends on this parameter Kasai. You see that exponential damping in the first yellow box. And if I refresh your memory again on the definition of this parameter, you can see that the nonlinear damping is weaker for higher magnetic field. This is because there's more energy in the initial electric field in a higher magnetic field pulsar. So that's harder to screen out. You can see that the damping is stronger for higher multiplicity. This is because more pairs are injected in the higher multiplicity plasma. You can see that it's stronger for higher period. This is because a higher period pulsar has less energy in the initial electric field. But the overall message here is that the damping is very strong overall. So in this stage, the electric field amplitude, which is meant to represent the amplitude of the electromagnetic waves that would actually exist in a real polar cap, this amplitude is getting very strongly damped. And this will basically complete in all pulsars. But this,
really fast. Sorry. Can you remind me why the longer period has less energy in the electric field?
This is because the electric field is generated through like the rotation, basically. So you get like a quickly spinning pulsar will have a stronger electric field.
Okay, right.
Also, just one more thing. You said higher multiplicity should have higher damping, right? But then I'm just trying to work through that. It has a lower psi there, I think, and then you end up having weaker damping, at least the way that you got it written there.
So there's a lot of negative signs here, right? So let's work through this, right? So if you have a higher multiplicity, you have a lower psi, which means you have a higher 1 over the square root of psi, right? Which would be a stronger damping, right? Did I get that?
Oh, sorry, I didn't see the oh, that's an exponent to minus 0.5. Okay, sorry.
Yeah, there's a lot of steps there. All right, but this exponential damping will only last so long. The question is why? So if we look at the evolution of the electric field strength as a function of normalized time, you can see that we've got a nice exponential damping that's in the orange dashed line, and it will stop at a point that's roughly called out by this blue arrow here. And after that, the electric field will not damp as strongly. So why does this exponential damping stop? So recall that the damping of the electric field is caused by the electric field reversing pairs injected at a momentum of roughly, say, 10 in the simulation and pulling them through a momentum of 0 or a Lorentz vector of 1. So in order for this physical process to occur, the oscillations have to have a strong enough field to give that much of a momentum change to the particles. Now, the amount of momentum imparted to a pair by a field of amplitude E star hat is E star hat over omega hat. So this is a parameter which is actually widely used in plasma physics, you can say. Some people call it a jitter velocity. Some people call it a wiggler velocity. I think there's other names for it as well. It's like a nonlinearity parameter. People have a lot of words for it, but
is this what in laser physics they call A naught, lowercase a naught?
Yeah.
Okay.
Great. So when this parameter reaches UL, then pairs can't be reversed, right? So basically, you can see the evolution of this parameter in our simulation in the second plot here, right? So initially, you can impart a very large amount of momentum to pairs by the electric field. Then as the electric field strength gets damped, the amount of momentum you can impart to the field is, the field can impart to the pairs is dramatically reduced as the electric field amplitude is reduced. And at a certain point, it'll get reduced to the value of the injection momentum. And at that point, pairs cannot be reversed. And this corresponds to the end of strong damping. So that can be seen in our simulations. Right. So after the strong damping ceases, there will still be some changes in the amplitude of the plasma oscillations, but these are sort of slight corrections on the overall determination. And so the rough magnitude of the emission is set by the amplitude of the waves at the point when the strong damping ceases. So to find the amplitude of the plasma waves, which might escape as radio emission, we can calculate the amplitude where the strong damping ceases. So I can do this in the blue box here, where I've unnormalized my units, and I've balanced the change in pair Lorentz factor with the injected pair Lorentz factor. And I put in a value of frequency typical for radio emission, and then you can find an amplitude of your plasma waves. Now we can consider how much radiation would be produced by emission at this amplitude across the polar cap. To do that, we just square the field and multiply it by the size of the polar cap. So I can do that in the orange box. And I get an amount of emission of 10^28 ergs per second, which is roughly consistent with the observed radioluminosity. So this suggests that the physics we've identified so far might be playing a role in why pulsars emit as brightly as they do. All right, so after this nonlinear damping ceases, we have this frozen phase 3, which is an artifact of the uniform electric field in our simulation, which you can read about in the paper, but it does end eventually. And then we have a phase with linear damping, which is phase 4. So that's at the end of this plot. So during this phase, yeah.
I'm sorry, I might have spaced out for just a minute, but so in the previous slide, you just described the balance. That's when at the saturation point.
Yeah.
When the electric field doesn't give the pairs more momentum than they started with.
Yeah, so this is roughly between phase 2 and 3 here. Yeah.
Okay, so you're saying that this saturation is an artificial consequence of the uniform E field.
No, so the saturation determines when phase 2 ends, and we think that this physics is very real in pulsars, and it sets the overall magnitude of the emission. But once the overall magnitude is set, there's still a little bit of change in the amplitude of the plasma waves, and that occurs in phase 4, and that's important as well. But when you run one of our simulations, there's another phase between 2 and 4, which is phase 3. And in this phase, actually, the amplitude doesn't change much at all. And it's this phase that is an artifact of the simulation setup. So 3, you can read about it, but it's just a simulation thing. So in the actual pulsar, you'd have phase 1, phase 2, and phase 4, basically. And we think that the physics occurring in 1, 2, and 4 is very real and very important. Great. So we have this linear phase 4 when the change in the newly added pair momentum is much less than the injection momentum. So pairs are not getting fully turned around. However, the wave amplitude and the frequency will continue to evolve a little bit due to the pair creation. So you should think of these evolutions as being sort of corrections on the overall emission amplitude, right? So this physics that occurs in the linear stage will occur across the polar cap for realistic electromagnetic waves. And at this stage, some of your waves will start to escape the plasma as radio emission. And across the polar cap, the emission will escape at different points in the damping with different values of electric field and frequency, right? So depending on where you are, you could escape early in phase 4, where you have a certain electric field amplitude, or you could escape in a certain frequency, or you could escape later in phase 4 when you have a different electric field amplitude and a different frequency. Now, so emission at these different points in phase 4 and a different across the polar spectrum, across the polar cap, these will all contribute to the emission that is observed on Earth. Right, so the relationship between the electric field amplitude and the frequency gives a spectrum, right? So the electric field and the frequency are governed by an equation that we've seen several times already in this talk, which I've repeated here in light blue. So there's a difference in this stage, and this is that the change in frequency is slow compared to frequency itself, right? This is not a condition that existed earlier on, because recall we had these very sharp spikes in the frequency from these pair bunches getting dragged through a Lorentz factor of 1. So when you have sharp spikes, you can't say the change in frequency is slow. We had to do a bunch of other physics. But now we can say that the change in frequency is slow compared to the frequency itself. So hopefully you hear a statement like that and like alarm bells go off in your head, because this is exactly the condition you need to be able to use the WKB approximation, which is sort of a bread and butter physics technique. So when you have an equation like this in blue with a slowly changing frequency, you just slam on the WKB approximation and you find that the electric field amplitude squared will vary as 1 over the frequency, right? So in this case, we have a slowly increasing frequency as you add more and more pairs to your system. So this will be a slow damping of the electric field amplitude. And this trend can be observed in our simulation, which is not very surprising, because again, this is a very bread and butter technique. So if emission starts to escape the paraplasma throughout this process, you could see this WKB relationship in the emission that you observe. And indeed, you see that the pulsar spectrum, which we introduced earlier in this talk, has a spectral index of -1.4 with a big spread on top of it. So this suggests that the WKB damping physics may contribute to the observed spectrum. I will note that there are many other effects that are important to the spectrum, including how any sort of modifications that might occur to the radiation as it escapes the plasma or on its journey from the plasma, to us. And there are, a lot of things there that we haven't considered. So this is, I would say, a tentative statement about the spectrum. It might be that some of this physics contributes to the spectrum, but there might be a lot of other physics as well.
Just one, this might be a kind of stupid one to ask.
Oh,
but,
there are no stupid questions.
I know, I'm just gonna still have to preface it, even though I don't believe it. But the thing, so if you go back a couple of slides, you said that, okay, you happen to mention that, okay, where a particular bit of radiation escapes depends on the field. And then that would be spatially varying across, let's say, latitude. If we say, okay, at the polar cap and then comes down. So if we monitored a distribution of pulsars, which all have their rotational axes at different angles as seen from the Earth, then would we see different spectra that you could kind of characterize using this physics and say, that would be kind of an observational test of this.
Right. Yeah. So that's an interesting thought that I hadn't considered. Right. Like if you get different cuts of the polar cap from different pulsar observations.
Yeah. And then basically this, wherever you predict that for that size of pulsar, whatever bit of radiation should be escaping from that bit that's directly angled at Earth. And then you see that, and then you build it up statistically across different number of pulsars.
Yeah, I think this would be a very, very interesting thing to do. My intuition, which is not actually very developed, but my guess would be that actually, different pulsars have different structures of their polar caps, and there's a lot of other changes between them that would make that a difficult project to do. But I think you could maybe make some progress there if you wanted to. I think it would be a little hard. Yeah.
Cool, thanks.
Cool idea. All right. So this is the key. We've gone through all the key physics in the paper. So just to refresh your memory on what we've discussed how pulsar radio emission may be created by electric field screening in the polar cap. We've studied this electric field screening to show that the radioluminosity might be understood as a transition from nonlinear to linear physics. And then we've seen that the radio spectrum might have contributions from linear damping. So as I've said before, this is all based on a published paper, which you can look up for much more detail. The slides of a talk very similar to this one are available on my website. There's also a recording of a similar talk there. And I as with all projects, this was really not possible without a large set of advice from people in the field and funding that I acknowledge at the bottom. So thanks.